Hello, everyone. I hope all of you are safe and healthy. And let's continue to finish chapter 10. Before we start, let's give a brief prayer. Dear Lord, here I pray that your peace continues to guard our hearts and our minds in Jesus Christ during the current challenging time. I pray that you continue to guide us in understanding general chemistry and then guide us in the online learning process and also guide us in our discussions. I pray in Jesus' name. In the last class, we discussed phase transitions. Let's look at the left figure. This figure shows the heating and cooling curve of water species. We can talk about the heating curve first. In the heating curve, the water species starts as a minus 10 Celsius degree ice. As the ice absorbs heat, the ice starts to increase its temperature, but still remains as ice, which is a solid form of water species. When the temperature reaches 0 Celsius degree, some ice starts to melt as the ice absorbs heat. The temperature of the mixture remains constant. Why is that? Here is why. In a mixture, the temperature is the same throughout. And then solid ice and liquid water should have the same temperature. So during these phase transitions, the water and the solid water, which is ice, and the liquid water should have the same temperature. The reason is because there's no ice that can be higher than 0 Celsius degree in temperature, while low liquid water can be lower than 0 Celsius degree in temperature. Then, during this phase change of ice into liquid water, temperature has to be 0 Celsius degree from the beginning until all the ice melt. Similarly, during the phase transitions of liquid water to water vapor, temperature remains 100 Celsius degree. The cooling curve is the same as the heating curve, but in opposite direction. In the cooling curve, during the phase transitions of water vapor to liquid water, and during the phase transition of liquid water to solid water ice, temperatures have to remain the same. But we need to keep in mind that this heating and cooling curve only applies when the pressure equals 1 atm. The heating and cooling curve could be different if the pressure is different. Now let's look at the right figure. In the last class, we also discussed vapor pressures of liquids. As the temperature increases, the vapor pressure always increases for all these three or four liquids. And when the vapor pressure is equal to the external pressure, here is 1 atm, the liquid start to boil. And here we can use water as an example. Water, you see, at 100 Celsius degree, is vapor pressure is the same as the external pressure, which is 1 atm. So the water boils at 100 Celsius degree. From both figures, we can see that both temperature and pressure matter in phases and phase transitions. A phase diagram can tell all the information. And that's what we're going to discuss in the fourth section of chapter 10. In this section, we'll first explain the construction and use of a typical phase diagram containing pressure, temperature, and phases. Second, we will discuss using phase diagrams to identify stable phases at given temperature and pressure, and then describing phase transitions resulting from changes of temperature and pressure. Third, we also touch upon the supercritical fluid phase of matter. Here is a typical phase diagram. Normally, it has three common regions. One is solid. The second is liquid. The third is gas. A typical phase diagram can indicate the physical states under specific conditions of pressure and temperature. For example, here we can use any pressure, but here we can just choose one. Okay, if the pressure is here, then as we can see, as we increase the temperature, this species can start as a solid. Then it can be converted to liquid, and eventually it will convert it to gas, right? From under this pressure, as we increase the temperature from here, then it can be converted from solid to liquid, and then from liquid to gas. Okay. Second, a phase diagram combines pressure versus temperature plots for liquid-gas phase transition equilibrium. Okay, here is liquid to gas phase transition equilibrium, and here is solid to gas phase transition equilibrium, and here is the solid to liquid phase transition equilibrium. And then for many materials, there's a critical point for each one. A critical point refers to a point beyond which the boundary between liquid and vapor phases disappear. At this moment, the species is not a liquid and is not a vapor either. So it has its own properties, and these properties are different from those of liquids and then gases, and we call such kind of phase a supercritical fluid. There's another important point which is called a triple point. At the triple point, three phases coexist in equilibrium. There's gas there, there's solid there, and there's liquid there, and all these three phases are in equilibrium. Here, we continue to use water as an example because we are all very familiar with water. Okay. Here is 1 atm. Here's the pressure 1 atm. Under 1 atm, you see here this is 0 Celsius degree, okay. Below 0 Celsius degree, here is a solid. And then from 0 Celsius degree to 100 Celsius degree is a liquid. This is what? This is the melting point. This is the temperature when ice melts into liquid water. And here, this is also the freezing point when liquid water is frozen into solid ice. Similarly, here 100 Celsius degree is the boiling point. At this temperature, liquid water boils to form water vapor. This temperature is also the condensation point when water vapor or gas is converted to liquid water. We need to keep in mind here the pressure and the temperature are not drawn to constant scale. You see here, here is the melting point, is 0 Celsius degree, okay, 0 Celsius degree. And here's the triple point. The triple point is here. The triple point has its temperature at 0.01 Celsius degree. So they are very close. Then we, to differentiate them, they are not drawn to the constant scale. And such kind of drawing is very common in phase diagrams. And here there are three kind of phase transition equilibrium. Here's a solid to gas or gas to solid, and here is liquid to gas or gas to liquid, and here is solid to liquid or liquid to solid. And a phase diagram can tell a lot of information. Previously, we discussed gas properties and liquid properties. Here, we move to discuss solids. First, we need to know there are two common kinds of solids. One is crystalline, the other is amorphous. Second, we'll discuss the main types of crystalline solids based on the bonds that hold the building units together. Third, we need to understand that the bonding and packing of the building units affect the properties of solids. For the solids, there are two kinds. One is crystalline, and the other is amorphous. Here, each ball is a building unit, and it can be a neutral atom, ion, or a molecule. In a crystalline solid, the building units are arranged in an ordered pattern, while in amorphous solid, the building units are arranged randomly. Here we talk about a few examples of crystalline solids and touch upon the lattice system concept. Sodium chloride is the major component of table salt we use in kitchen. It's an ionic solid. The reason why we call it is an ionic solid is because the sodium ions and chloride ions are held together through ionic bonds. At the atomic level, sodium ions and chloride ions are packed in a cubic way. As many of them are packed, a cubic sodium chloride crystal can be formed. This is the cubic crystal that can be seen by optical microscopes or even by our naked eyes. That's just one example how properties at the atomic level can affect the properties of a bulk materials. Copper is another kind of solid and is considered a metallic solid. The reason why it's considered a metallic solid is because copper atoms are held together through metallic bonds. As you can see from these two, the atoms or ions, here we call building units. The building units are packed in the same fashion. So we call these two materials have the same lattice. Both ionic bonds and the metallic bonds are very strong. So these strong bondings can hold these building units very strongly. That's the reason these two materials have very high boiling point and a very high melting point. And at room temperature, they both exist as solids. In contrast, carbon dioxide here is an intermolecular force solid. In this solid, each carbon dioxide molecule is a unit, and many of them are held together through intermolecular force, which is quite weak compared to ionic bonds and metallic bonds. So that's the reason all these carbon dioxide molecules are not held together very strong. So carbon dioxide has a much lower boiling point and the melting point compared to sodium chloride and copper metal. Previously, we just discussed three kinds of solids, right? The ionic solid and metallic solid and the intermolecular force solid. And here's the fourth crystalline solid that is called covalent network solid. A covalent crystal contains a three-dimensional network of covalent bonds. So here are four examples, and I will discuss two of them. The first is diamond. Here is diamond. Diamond is made of carbon atoms that are tightly connected to each other. It is very stable and does not react with other materials. In other words, it can last forever. To some extent, graphite is an outlier. It is composed of planar sheets of covalent bonds. You see, in this, there are many layers. And they are identical. All these layers are identical, and in each layer, the carbon atoms are connected to each other through covalent bond. Unlike typical covalent solids, graphite is very soft. The reason is because these layers are held together through intermolecular forces that are quite weak. As we write using pencils, these layers are peeled off stepwise. Besides, it is electrically conductive, and it can be used as electrode materials in lithium-ion batteries. And in organic chemistry, we can understand why graphite is conductive. Here I just discussed two examples of covalent network solids, and we can see how their structures at the atomic level can affect their overall physical and chemical properties.